the radius, and that's going to make a difference. It's going to give us a fourth power here and a sine cubed here. So this power is going to turn into 4. This power is going to turn into a 3, and the same is going to happen down here. We're going to get a fourth power here and a third power here. So we'll make a note here. Reconcile this expression with the expression we should get here. We got to square the r in the mr squared expression for moment of inertia. Now we'll go ahead and calculate the integral, the correct integral for the moment of inertia. So in the preceding we integrated what turns out to have been the wrong function for the moment of inertia. I noticed that we had an r to the fourth here instead of an r to the fifth. And from the physics of the situation, knowing the moment of inertia of a uniform sphere, this just didn't reconcile. The power of r didn't reconcile. The constants didn't quite reconcile, but the power of r is way off. At least off by 1 order of magnitude, or 1 power of r. So to reconcile, we had to square the r and the mr squared, and that is going to result in this integral. So let's go ahead and calculate this integral, which turns out actually to be even a little easier to calculate than the preceding. So we can do this rather quickly. This is an integral from 0 to pi, 0 to 2 pi. We're going to get 12 rho to the fifth minus 9 rho to the sixth over r. That's going to give us, 12 rho to the fourth minus 9 rho to the fifth over r. Our antiderivative is going to be rho to the fifth over 5 here, so we're going to get 12 rho to the fifth over 5 minus 9 rho over r times rho to the fourth is 9 rho to the fifth. That's going to give us 9 rho to the sixth over 6 times r, evaluated from 0 to r. And then that's going to be integral of sine cubed phi d theta d phi. This expression comes out 12 rho to the fifth over 5 minus 9 rho to the sixth over 6 r, 12 r to the fifth, not rho to the fifth, giving us 12 r to the fifth over 5, and then 9 r to the sixth over 6 r is going to be 3 r to the fifth over 2. Our integral of d theta from 0 to 2 pi is again 2 pi. Then we got the sine cubed phi d phi. So this all comes out to what? 12 fifths minus 3 halves. Our common denominator is going to be 15. That's going to be 36 over 15 minus 15, it's not 15, 5 and 2. Common denominator is going to be 10. It's going to be 24 over 10 minus 15 over 10, which is 9/10. R to the fifth multiplied by 2 pi multiplied by the integral from 0 to pi of sine cubed phi d phi. Easy to integrate sine cubed phi. We simply write that as sine phi times 1 minus cosine squared phi. Let u equal cosine phi, so that du is going to be negative sine phi d phi. That's going to come out with a simple short result. So I'm going to kind of box off here and do that integral. The integral, well, antiderivative. Let's just do an antiderivative of sine cubed phi d phi. equals an antiderivative of sine phi times 1 minus cosine squared phi. Make sure I got the edge of the paper there, d phi. Let u equal cosine phi, so the du is negative sine phi d phi, so that now our integral simply becomes the integral of negative of 1 minus u squared du, which is going to be u minus u cubed over 3, but that's negative, so it's going to be u cubed over 3 minus u. U having been set equal to the cosine cubed theta, that's going to then equal cosine cubed theta over 3 minus cosine theta. If that's correct, and I hope it is, the integral of sine cubed phi d phi will then be this expression evaluated between 0 and pi, so that what we should end up with, and I'll keep these factors separate just so we can again trace them back and or relate them to what we've seen before. This is going to be cosine cubed phi over 3 minus cosine phi evaluated between 0 and pi. Had to squeeze that in a little bit. I should have given myself more room. But this is pretty straightforward. We just substitute 0 and pi. I'm not going to take the time to write this out. Simply going to say that when theta equals pi, the cosine of theta is, cosine of pi is negative 1. The cube of negative 1 is negative 1, so we're going to have negative 1/3 minus negative 1, which is going to give us positive 2/3. At 0, the cosine is equal to 1, so we're going to have negative 1 plus 1/3, which is negative 2/3, but we're subtracting that. And as a result, this integral here is just going to give us 4/3. So we're going to have 9/10 r to the 5th multiplied by 2 pi. And that's equal to, 2 divides into 10 5 times. So we're going to have a 5 times 3, 15 in the denominator. So the 3 goes into the 9, so we'll have a 3 over 5. And I've already lost track of what I just said. It's going to be 3 times 4 is 12 pi over 5 r to the 5th, which equals 2.4 pi r to the 5th. Now let's compare that with what we would have gotten from uniform sphere mass 2/5 mr moment of inertia 2/5 mr squared. That gave us 14/5 pi. This gives us 12/5 pi. Remember I said previously that since the mass is more concentrated toward the center, the moment of inertia will be somewhat less than predicted by a simple 2/5 mr squared based on a uniform sphere of equal mass. Our result seems to confirm that. We get 2.4 pi r to the 5th as opposed to 14/5 pi r to the 5th, which would be 2.8. So that reconciles pretty well, leading us to think that we might possibly have gotten this right.